Thank you all for joining us for our next Dorsey Power Hour event. Today we'll be doing kitchen ventilation systems presented by Ryan Stewart. Real quickly, I just wanted to introduce our engineering support team at Dorsey, which includes Scott Boucher of our Seattle office, Blake Bonham out of our Spokane office, and myself, Chris Woldridge, who I'm sure you've all seen a ton of emails from over the last month or so promoting our Power Hour. A couple of housekeeping rules real quick. We have everyone muted and cameras off. So if you have any questions, please put it in the chat. I will be moderating those and answering as I can. Otherwise, we'll most likely hold off till the end and allow Ryan to answer all the questions at the end of the event. But please ask questions. This event is for you to educate you, our customers, on everything Dorsey has to offer, and also the basics of kitchens and the fundamentals of a good ventilation system design. So Ryan, with that, I'm going to let you take over and kind of introduce how you work with all of us at Dorsey and give your background.
Perfect. Thanks, Chris, and thanks everybody for joining us today. A little bit about me. I've been in the kitchen ventilation industry for 25 years. So I have experience with various brands and products associated with kitchen ventilation. Over the years, I've designed and supported thousands of systems throughout the US and Canada, from individual design build restaurants to major national chains and all kinds of custom applications in between. Areas of expertise are going to be kitchen ventilation design, mechanical, fire, and energy code. And there I've listed a lot of the products that are incorporated into a kitchen hood system. So to start off, I just want to kind of briefly touch on the codes. Since there's so many products that are incorporated into the system, they touch a bit on everything. The big one's going to be International Mechanical Code. Then you have NFPA 96 for standards associated with kitchen ventilation and fire protection. Various UL listings depending on the products. UL 710's big for hoods, UL 300 for suppression, 705 for exhaust fans, and then there's some new listings for pollution control equipment. You have energy codes, fire codes, building codes. The ASHRAE 90.1 is a big one, and then Washington State Energy Code. So hoods, they're going to fall into Chapter 507 of the International Mechanical Code, and there's going to be two types of hoods. So type 1 is going to be grease-producing appliances. So the cooking process produces a grease-laden vapor or smoke. And so some of those appliances are going to be griddles, fryers, ranges, broilers, woks, and etc. And then there's type 2, and those are going to be for heat and steam. Cooking process produces no grease-laden vapor or smoke. So that's going to be your dish hoods, steamers, kettles, pasta cookers. And then there's appliances that kind of fall into a gray area. So if you're looking at an application where it's just an oven, then you need to determine what are they doing with that. Is it a bakery, bread, pastries, those type of things, no smoke or grease-laden vapor, then potentially a type 2. In a lot of cases, those ovens are going to fall into a type 1 hood. So the International Mechanical Code says that any hoods that are built in accordance with UL 710 shall not be required to comply with the following sections. I think the important ones to take a closer look at are going to be the hood size, location, and then capacity of hoods. So this just gives you an outline of how much of Chapter 507 a UL 710 hood is exempt from. So let's start out with some of the different types of hood. Top center, that's a wall canopy hood. That's going to be the most common hood that you're going to see, typically installed 80 inches off the finished floor. You need to have a minimum ceiling height of about 110 inches to fit a hood like that. You may see island hoods in restaurants where they do display cooking. In applications where you don't have the 110-inch ceiling height, you might be looking at some type of a tapered canopy hood. And then real low ceiling applications, you'd be looking at a passover, backdraft, or crossover hood. So you might see those in like food trucks, sometimes in diners, older buildings. They're going to limit you to standard 36-inch cooking surface height appliances. You're not going to fit ovens and those type of things into hoods like that. And then I showed the auto scrubber hood. I'll talk a bit more about that when we get into pollution control. So as far as type 2 hoods are concerned, this is 3 different configurations. The most common is going to be the one on the top there, just a standard canopy. It's going to have a full perimeter gutter with a drain. The idea behind the other 2, they have condensate baffles in there. And when initially designed by manufacturers, they thought, oh, these would be good for high steam applications. We can, it'll condensate on the plates, allow us to remove more of that from the airstream. And what we've kind of found out over the years is those plates take up so much of the containment area that those high steam applications where they thought they made sense, it really drove up the airflows. Otherwise, the volume of steam would overwhelm the hoods and they would spill. So most common, again, is going to be that one on the top. You'd see that over a dishwasher, ovens, things that produce no grease-laden vapors. These are not going to be UL listed. They're going to have an NSF listing for sanitation. So I wanted to put up a map here that shows what states have adopted the ASHRAE 90.1 2019 standard. As of the end of 2024, there are 14 states on this standard. So you can see most of the West, we're primarily doing work. That's all going to be on the 2019 standard. So what's that say about exhaust airflow for commercial kitchen hoods? I've listed on top's the ASHRAE 90.1. I'm going to reference the Washington State Energy Code. I think that applies to more of the projects here. But basically it says if the total exhaust CFM for the hoods is greater than 2000 CFM, then you need to have a UL 710 listed hood. And then you need to refer to a table that references by appliance duty what your maximum CFM is for that appliance duty. So you're going to look at the heaviest duty cooking appliance under each hood to determine the duty. So here's an example of that table. You'll find down the left side your different types of hoods, wall canopy, single island, your various types, and then across the top what those appliances duties are. And then it's going to give you a maximum airflow per linear foot for each of those appliance duties and hood type. So as far as the appliance duties are concerned, you can reference Chapter 2, the definitions in IMC. For each of the duty classes, it's outlined what appliances fall into those classes. And I put that into a table here, and then included what International Mechanical Code has for minimum airflows for the appliance duty. Again, these UL 710 hoods are exempt from that section of the code. The next line down is what your maximum flow rate is per foot for the appliance duty to meet Washington State Energy Code and ASHRAE 90.1. And then down at the bottom is the UL 710 minimum airflows for those appliance duties. A design airflow, you're going to fall someplace in between UL 710, which is your perfect world lab condition, and what code says your maximum is for the appliance duty. So here's an example of what you might see. If we have kitchen consultants on the phone or kitchen designers, this would be a plan that they would put together. So you'd want to reference this plan and then the equipment schedule. You'd look through here and see what your heaviest duty appliances is, determine your appliance class and duty, and go from there. This example, this is a 15.5 foot hood. It could be built in one section. Most of the major manufacturers can build up to 16 feet in one section. What I've found over the years, especially with existing buildings, is it's pretty difficult to get a hood that large into the building and back into the kitchen area. So usually over 12 feet, I'm going to design a hood as 2 sections. with a continuous capture. So if you'll notice from the image there, that hood, it's two hood sections, but there's no wall inside the canopy itself. And what that's going to do is give us the greatest containment area and the lowest possible airflow. So I've divided this up. I have a 7.5-foot hood on the left. It is a heavy duty by appliance classification because of the range. But based on what we have there, I'm comfortable at 230 CFM per foot. We have that wall on the left-hand side, so that's helping with capture and containment. And then the right side, we have that large charbroiler. That's where you're going to want to be up near the maximum that the code allows. And by doing this two hood approach, we've netted a savings of 375 CFM. So overhang, that's one of the things as airflows have been pushed down by energy codes. International Mechanical Code, as long as I can remember, has always said 6-inch minimum overhang on all open sides. And I think that, well, the exception to that is if you have a wall or some sort of a containment panel, then you can get reduced overhang. What I've seen over the years is the industry's done a pretty good job of getting more front overhang on appliances. It's rare that you see a hood designed with 6-inch front overhang. But as far as the left and right sides of hood, it's pretty common to just have the 6-inch overhang. In FPA, they don't specify a specific overhang. They just say that it needs to be sized and configured to provide capture and containment of grease laden vapors. So what I tell people when I look at jobs is, if you think about making a hood 12 inches wider or deeper, it's really only 4 square feet of sheet metal. So it's a pretty minimal cost up front to have major benefits for the life of the system. When you're looking at appliance layouts, if you have real heavy duty cooking appliances out on the ends of the line, that's where you want to push to have 12 or more inches of overhang and not just go with the minimums. Appliance type matters. So you're going to want to look at those plans or talk to your customer and figure out, what appliances are going to go under their hoods. Ovens, you think, they're kind of a lighter duty appliance, but with the front doors on those, when you watch them operate and they load and unload product from the ovens, that heat plume will come out 18 to 24 inches. So it's important to have as much overhang as you can for that situation. Island hoods are another one where you're going to want to look at higher airflows and additional overhangs. You don't have the walls, the back wall or side walls to alleviate some of the drafts around hoods. And so you need more overhang to compensate for that. So this slide here just illustrates what I was talking about of suggested overhangs at the front and sides of various appliances. So capture and containment panels. So a hood with 6-inch overhang, as that convective heat plume rises, it's going to expand. And you can see from the illustration there, there's a good chance that some of that hood is not going to be completely captured by the, or some of that convective heat's not going to be captured by the hood. So you can add stainless steel containment panels to help force that up into the hood. They can also help alleviate drafts from doorways, walkways, things that are happening inside the kitchen. This is a Schlerin camera. I'm going to show this video here, and you can see the convective heat plume comes about 2/3 of the way out from the hood. You can actually see convective heat spilling out the front face of the hood. They're going to walk over and add some panels here. And what you'll notice after these come on is that convective heat plumes move back to probably the back third of the hood. So it's all the way back underneath the hood here, and now you're not spilling anything from the front anymore. So just the addition of a few $100s worth of sheet metal panels have significantly improved the performance of that hood. These are the most common configurations you'll see from various manufacturers. The minis, I think, are the ones that are most likely to be installed. The insulated vertical panels there in the middle, that's a great option, but you really need to look at how the appliance line lays out. If there's tables and things like that that are going to interfere with those being installed. Um, and then the final one there is the full skirts. And the challenge with those are line of sight, workflow from appliances over to prep tables. So those you don't typically see something like that. So clearance to combustibles. This is out of the NFPA 96. Let's see here. So as a manufacturer, if we're aware of surfaces near the hood that are combustible, we can add insulation, and we can add it to the back, top, left, right, front, pretty much any surface. When we do that, the manufacturer's UL listing will indicate that that surface rated for zero clearance to combustibles. So this is just another example of that. And what the code says about it. Basically, all surfaces within 18 inches of the hood need to be non-combustible, or they need to be protected. Another way that you can accomplish this is with an insulated pad. So that would consist of a 1-inch mineral wool insulation covered with stainless steel cleanable surface. And you would install that the length of the hood and 18 inches beyond. And I've seen that, put on ceilings and those type of things. Ideally, you do what you can to have all materials within 18 inches of the hood be non-combustible. So as far as exhaust fans, there's various types just depending on the application. So your typical standalone restaurant, straight duct run, you're going to see upblast fans. In applications where you have more extensive duct runs or potentially duct going up fire shaft, then you might see something like a utility set fan. And then in some applications, you end up with some type of a grease rated inline fan. The industry is changing from UL 762 grease rating over to UL 705. So you'll start, currently it's a dual listing, but you'll start seeing the UL 705 grease on the labels on the fans. For the most part, for kitchen ventilation, everything's converted over to direct drive. One of the things I'd like to point out, if people have been to Greenheck, they've seen this. They're an AMCA member. And so in their R&D facility, they have AMCA certified test chambers for airflow and sound performance. And because of that, they're able to really test the fans to the highest level. They have some of the most efficiency and high quality fans in the industry. And that's unique from a kitchen ventilation standpoint. I'm not aware of any other manufacturers that have AMCA certified test chambers for their fans. This is the most common. A couple of the nice design benefits with the Greenheck is this outer band here. It is all one piece. It's stamped construction. And then the base of it is robotically welded down here. And so you get a good leak-proof construction. And then they have a nice grease containment system to go along with it. As far as motors, Greenheck, if you're familiar with their products, they do the Verigreen EC motors. They have single phase up to 2 horsepower and then 3-phase up to 10 horsepower. And then they also integrate on some of the larger ones, Verigreen drives that go along with those. So Washington State Energy Code has a requirement for fan energy index of not less than 1.0 at the specific design point of operation. This is going to apply for any fans that are over 1 horsepower. So what this does is it's a ratio that's going to allow you to compare the energy consumption between similar fan systems, various models and manufacturers of fans. It's there to help you select the best fan for the system and application. And it is a mandate in any of those 14 states that are on ASHRAE 90.1. So it's something that you're going to start to get requests from jurisdictions to have FEI as a part of your fan schedule. So what is it and how is it calculated? So they're looking at a comparison to a baseline fan's electrical input at that duty point to the actual electric input for the whole fan power system. So what you'll see there is a fan curve down on the bottom left, and you can see fans that are in the peak part of that curve are going to have the higher FEI rating, typically lower RPMs going to net and a higher FEI. So in comparison to brake horsepower measured fan power at the shaft, but not for the full system. So it didn't include the loss from VFDs, motors, and drives. And I want to share this example here. This is out of caps, and you'll see this is 3,500 CFM at a 1/2 of an inch static pressure. The like wheel sizes, the 160s, 180s, 200s, those are identical wheels. When you look at this, everything appears to be equal, even brake horsepower, RPM for the like fans. But if you take a closer look at the FEI, you can see that that varies. For comparison, like a fan that's at a 1.21, what that means is that fan is 21% more efficient than the code minimum baseline fan. And in this case, the reason that fan's the most efficient, at least for that size, is because of the EC motor. On the left there, I've given you an example of what the UL label says. So as a manufacturer shipping fans into states that have the requirement, they have to label the fan that shows what the performance is that meets the minimum 1.0 FEI requirement. So codes related to controls, they require an interlock, and they want it to be automatic. So they give you basically 15 minutes from the time that an appliance turns on and produces heat to activate the fans. And they want the exhaust and supply fan to turn on together, so no separate switching's allowed. And then in fire condition, they want to see that the gas and electrical turn off and the exhaust fan runs to full speed and the makeup air shuts down. This is just the section out of IMC that that talks about that in more detail. When you have multiple hoods on a single fan, each of the hoods is going to need a heat sensor. And if there's heat under any one of those hoods, the system needs to turn on within 15 minutes. So ASHRAE 90.1 and Washington State Energy Code, they require demand control ventilation if the exhaust airflow is greater than 2,000 CFM. And they say that it needs to be configured to provide a minimum of a 50% reduction in exhaust and supply air in response to the appliance operation, while maintaining full capture and containment of smoke and grease-laden vapors. They do offer an exception. So hoods that are less than 5,000 total CFM and less than 250 per foot for airflow, they are exempt. What I will say on that is when you think about the hoods do require a temperature sensor for the auto activation. Most of the fans are direct drive, so they have EC motors and VFDs already. It's a minimal cost increase to have the demand control ventilation, and you get significant benefit from it. So this just shows the various components associated with the hood system. There's a sample of what the control box would look like. The Greenheck one has a color touch screen, real user-friendly, easy to understand and operate. So how it works. So there's two options. You have a room temperature sensor that's measuring actual room temperature, or in cases where a condition may not be, or a kitchen may not be well conditioned, you can do a preset temperature. So based on a 75-degree room temp or preset, once the appliances turn on and it produces more than a 10-degree rise in temperature, it activates the system and it brings it on at its 50% airflow. And then it has a modulation temperature range. So factory setting is going to be 115 degrees, but that's adjustable depending on the appliance type. and it's going to modulate airflow throughout the day based on what the temperature is underneath the hood. As far as shutdown's concerned, it wants to see the temperature drop 5 degrees below the activation point for 30 minutes before it shuts it down. And the idea behind it is they want to give the appliances time to cool. So when it loses exhaust, you don't short cycle the fan. Kind of the next step in demand control is adding an optic sensor. And this is something that it's been available from various manufacturers over the years. Greenheck's just added this to their line. And what it does is it gives the system the ability to look at smoke. So it's sending a beam from one side of the hood to the other. It just gives a faster response when you have flare-ups or when you throw product onto a cooking surface. So to give you an example where you might look at something like this over the baseline system, let's say you have a large charbroiler and it's at an idle condition. So the demand control is running near its 50% speed. When you first throw a bunch of like product onto the grill, it's going to have a cooling effect, all the cold product that you just put on there. But what's going to happen from a cooking standpoint is the sear is going to produce a bunch of smoke. And so those sensors are going to give that instant reaction to the smoke to start ramping the fan speed up more rapidly until the temperature sensors can catch up. The standard DCV, the way that they've handled that is having 100% override. So the staff would understand, hey, when I put this on here, we're going to have more smoke produced, or I've burned something and there's a bunch of smoke. They can hit the 100% override. It pushes the fans to full speed for 30 minutes, and then it'll look back to the heat sensors in the hood. As far as savings concerned, a 50% reduction in airflow is an 88% reduction in the cost to operate the electric motor. Where the biggest savings is actually in the makeup air though. When you're at a reduced exhaust, that's also the supply, so it's less air that you have to heat and cool. So that's where you see some of the biggest savings. Through PSE, there's some programs around here for retrofits. So if you have restaurants that are interested in control upgrades, in some cases, the rebates can pay for the full cost of the control panel. One thing that's critical when you're doing demand control, in some cases, maybe the kitchen consultant specifies the hoods. The engineer's responsible for selecting the mechanical equipment to go along with that. It's important that you get a makeup air unit that's configured for variable air volume and that's capable of a 50% reduction in airflow. It's not an easy thing to do. And so you should always check with the manufacturer you're working with to get the minimum airflow and make sure the makeup air is going to work with the hood controls. I've been with Dorse for a year now. I've done quite a few designs with the Greenheck products. And so far, there haven't been any applications I've found where the Greenheck makeup airs aren't capable of the 50% reduction in airflow. Makeup air and delivery options. And this is a real important part of having a hood system that works well is how you're introducing the makeup air. So most common, you're going to see a compensating hood that has some type of a perforated plenum that runs along the length of the hood, and then potentially even wrapping around the left and right open sides. If you have a real high exhaust airflow, you may need to wrap those around the sides to have correct velocity of makeup air. This Greenheck one, they use a slotted perf, and what they just found from testing other GRD stuff that they built, that this was most effective at reducing the velocity of the air and dispersing it evenly across the length of that plenum. So traditional design that you'd see, you'd have your RTUs in the dining area. They're controlling space temperature and humidity and providing the minimum outside air requirements based on ASHRAE standard 62. And then back in the kitchen, you would have a makeup air unit. Code says it needs to be capable of providing 90% of the exhaust, but you typically see in the 80 to 90% range. You're usually going to condition the makeup air within 10 degrees of space conditions. So Western Washington, you're going to heat it, potentially do some cooling. Eastern Washington, you're going to see heating and cooling. And as a part of that makeup air, the way it's introduced with the compensating hood is it also does help provide an air curtain to aid with capture and containment. And then you have an RTU or ducting from RTUs that help condition the kitchen area. So these are just a few of the makeup air options from Greenheck. You could do untempered, electric heat, hot water, steam, pretty much any configuration that you need. It's also available in direct fired gas, various cooling options from packaged DX to evaporative cooling. And then you do have indirect fired. You don't see that as much anymore. One of the things that I'll kind of caution against the indirect fired is the standard ones have like a 4-to-1 or 6-to-1 turn down. So your minimum temperature rise can be rather high because of that. When you start to factor in that during idle conditions, you could have a 50% reduction in airflow, and then you have that minimal turn down. In some cases, I've looked at these and you're turning on heat below 60 degrees and your minimum temperature rise is 25 or 30 degrees. So right away, you're overheating the kitchen. So just be careful if you're looking at the indirect product line. This unit here is unique to Greenheck. As far as I've seen, they're still the only manufacturer that's offering a direct fired makeup air that has packaged DX cooling with the R454B refrigerant. This one right now, it's single stage, limited to 10-ton capacity. It's available from 800 to 5,000 CFM, and it's capable of the full 50% modulation range. This one, it's designed for sensible heating and cooling. So again, we're going to turn on the heat below 60 and turn on cooling above 75. And there in the center is an example of how they're able to accomplish the 50% reduction in airflow. It's utilizing a face and bypass damper. So when they go to the 50% airflow, they close that damper, forcing all the air across the burner so they maintain a good differential pressure and a nice clean burn. So another option for makeup air is going to be utilizing an RTU or a DOAS. And this is something that's become more popular over the last few years because of the advance in these products. Now we have RTU and DOAS that can handle conditioning full 100% outside air. And so the idea behind this is rather than have a makeup air and an RTU, you have one unit that handles both the heating and cooling for the kitchen and the outside air. So when you look at that from a cost standpoint, yes, these are more expensive than a typical RTU or a makeup air unit, but you've eliminated the 2 duct runs, the 2 roof penetrations, the electrical associated with it. Big picture, you get pretty close, and there's some really good benefits from a comfort standpoint and efficiency. And this is a recent release from Greenheck. It's a new RTU that's designed to handle larger volumes of outside air. When they develop these kind of things, they look worst case scenario down in the South, very hot and humid. I've looked at a bunch of these for our area, and they work really well at 100% outside air. And so it's a good approach, not as complex as their RV line. And so it's a more cost-effective approach for kitchen makeup air. So what's it look like? This would be an example where you have an open kitchen, open to the dining room. All the supply air is going to be introduced through ceiling diffusers in the space. You eliminate the compensating hood and you use low velocity, non-directional ceiling diffusers near the hood. It just provides a higher level of comfort for the kitchen staff and the people in the dining area. And when you from a hood performance standpoint, the UL listing or the the UL testing that they've done, when they've achieved the lowest airflow is with non-compensating hoods, just standard exhaust only, all the makeup airs being introduced away from the hood at low velocity. That's the best outcome as far as lowest air volume for the hood. So you get some additional benefit from lower exhaust airflows with this approach. This would be an example of the diffuser from Greenheck. It'll be under their metal air branding. This is out of their healthcare laboratory and clean room. It's a low velocity, non-directional diffuser. The standard is it's a white finish, so it looks good in a grid ceiling, or it can be configured to go into a sheetrock ceiling. We don't want to see any directional diffusers within 10 feet of a hood. We also don't want to see any HVAC returns in proximity to the hood. Ideally, for best performance, you're looking for a 0 velocity at the cooking surface. From a control standpoint, for these makeup air, these more advanced makeup air designs, these units will have microprocessor controls. And so they'll be factory configured with a few different ways to operate. So during an unoccupied period, if you get a call for heating or cooling, it would just run full recirculation. Maybe in the morning, you have people in there working, but the hood's not on yet. So it would have a mode for that where it'd have a minimal outside air position, and then the rest would recirc. And then when the hood system comes on, full occupied mode, 100% outside air. So PCUs, these are going to be a big thing, like in Bellevue, Seattle, some of your bigger cities. You used to only see them when code mandated it, but more and more we're seeing building owners want to put these in to avoid complaints from the neighbor, just provide cleaner environment or cleaner air into the environment around the restaurant. And over the past few years, they've actually developed standards specific to pollution control units. So UL 8782, that's going to be specific to PCU construction, materials, and electrical. Previously, they just tested the units to a UL 1978 standard, which was for UL grease duct. And really all they were looking at is the cabinet construction. The new listing requirements, they're looking at the unit tested under extreme loading conditions, which is what you're going to have from grease buildup. And now you'll see in Chapter 506, which relates to exhaust fans, that they'll reference these UL requirements for pollution control units when they come up. And then there's a separate one for electrostatic precipitators. So pollution control application. If you have an application like this, the first line of defense is going to be your hood filters. The standard from Greenheck, we're typically going to go with an extractor filter always. In most cases for a PCU, we'd stick with that same filter. It's something that's easy enough to maintain by the restaurant staff. There is an upgrade. The grease grabber filter, it's a 2-stage filter. And so the second stage is a porous ceramic bead. It does require a lot more maintenance. So they offer a scrubber hood where there's actually a wash system in the hood to clean that ceramic bead bed. So this is going to be one type. It's mechanical filtration. We're going to look at the cooking equipment lineup. I'm going to ask questions about what the discharge is like. Are we discharging into an alley? Are we discharging near, residential condos, operable windows? And then we're going to figure out how much filtration do we need. So it can be configured with 3 or 4 modules. We can configure filters for each module based on the application. And then the final stage of it is going to be a carbon tray to absorb the remaining odors. So this one, they're configurable from 3,000 CFM. I think just recently they released a larger one that goes up to 17,000 CFM. All 16 gauge stainless steel construction. They're going to have a UL 300 fire suppression, and then they're going to have the 8782 listing. The next step up is going to be the grease trapper. This is going to be for applications that have heavy smoke. So it's using electrostatic cells. They're capable of removing up to 95% of the grease down to 0.3 microns. So that's going to be your smoke particulate. And then they're configured with a wash system. So once the cells collect that grease at the end of the day, it'll go through a wash system and rinse it off those collection grids. So this is what it looks like assembled. In a perfect world, we put it together from the factory. So it's all factory assembled. You'll have your wash manifold put together, the drain put together. You can have the control cabinet mounted onto the rails. Everything's factory wired. The reality is these things are huge. And a lot of times it's difficult to get these into a building in one section. So they can be shipped in individual pieces. The electrostatic ones, since they have a wash system, they need to be welded back together continuous. So it's a pretty extensive process to put them together in the field. The filtration one is listed to be bolted together. It doesn't have a wash system. And so they've been able to get a listing for that. So how's it work? So it's using 12,000 volt ionizer plates to positively charge the airflow as it comes into the unit. And then it passes over 6,000 volt negatively charged plates, which attract those positive charged particles. They stick to the plates. And then at the end of the day, that's what gets washed down. So you have a fresh start the next day. Again, just like the other PCU, once you've removed the grease-laden vapor and particulate, then you have carbon trays to absorb the odor. Various configurations of fans. This would be an application where you may still see some belt drive fans because they're going to be high CFM and traditionally high static pressure. Most common, I would say, utility sets. They're most configurable, but in some cases, the inline fan is a good fit for it as well. Another option where maybe a full-on PCU isn't required by the jurisdiction, but there's concerns about odor or like grease mitigation. They don't want to see grease on the louver of a building, or this would be another thing for retrofit, but it's using UV to produce ozone. It's very effective at reducing odors from grease-laden vapor. And it's also does a good job of reducing the volume of grease in ductwork. The important thing with this is it needs time to react. So the longer the duct run, the more effective this approach is. The manufacturer recommends a minimum of a 3 second reaction time. But again, the longer the duct run, the better. And what you're going to see here, if you do have those real extensive duct runs, is much lower risk of fire, reduced duct cleaning requirements, reduced grease buildup on the louvers so the outside of the building looks nicer, and then of course the reduced odor. And these are pretty small in comparison. So again, they're easy to retrofit. And this just gives you an idea of how it ties in. So you'd have this tap into the grease duct right near where the hood is. The exhaust fan for the hood system will pull the 70 CFM through the ozone generator and to get it into the ductwork. Some of the components that go along with it, you're going to have a fire damper. So if there's a fire in the grease duct, it can't spread into this unit off the side. And then you'll have a balance damper so you can control the volume of air across those UV bulbs. So you have the right concentration of ozone to be effective at reacting with the grease. So type 1 hoods, the code says that they require fire suppression. It needs to be an automatic fire suppression system. And then they reference chapter 9 of the code book, which basically says it needs to be a pre-engineered automatic dry or wet chemical system tested in accordance with UL 300. I'm not aware of any dry chemical systems associated with hoods. Pretty much everything's wet chemical or even some sprinkler-based systems. They require a manual activation device, so they'll operate automatically off of fusible link or heat detectors in the hood, but they also require a manual activation device. They want it not less than 10 feet from the hood, no more than 20 feet from the hood, and they like to see it in the path of egress. So if you have a fire under the hood, as you exit the kitchen, if the system hasn't automatically activated, you can pull the pull station and manually activate it. So there's two types. There's appliance specific, where the nozzles are specific to the appliance type. It has a specific position that it needs to be in to protect that appliance. And then there's overlapping coverage. Greenheck works with both Ansel and Amorex. They each have their own benefits. Both of them have a great distribution network for installation, service, and those type of things. For the most part, detection for these systems is mechanical. We have started to see some manufacturers push electronic detection into it, where you'll have electronic fire stat, electronic pull stations. They're great systems. The one thing that I think needs more support is traditionally the fire subs have been plumbers. They hook up the pipes, they're able to run the detection line, do the pull station. When you add in the electric aspect, now you have somebody, it's basically pulled the part that makes the system work out of their scope. And a lot of times it's being pushed into like the electrician or the low voltage contractor scope. They don't have a ton of experience with fire suppression specific to hoods. And so it's just not supported as well as it could be. I think it's something that as the industry progresses, it will be better, but that's one of the challenges that I've seen with it now is just a lack of support from a installation and service after installation. So grease duct's another big part of it. We work with Jeremias, and they've been building various duct products since 1970. They've been in the U.S. since 2012. They're based in Georgia. And this is a photo of Atlanta Braves Stadium and some grease duct runs there. What's unique about them compared to others, and they still build this as well, but there's a flange type product where you put a high temp sealant between the flanges, and then you put basically once you get that done, you put a clamp around the outside, a layer of insulation, versus Jeremias is the only one that offers a slip connection to where the caulking goes on the outside of the duct. It slips in there and it's complete. So you don't have the extra insulation cookie that goes along there. One of the other benefits is all the insulation is on the inside here, so none of it's exposed during duct cleaning. And you have less, you don't have any sealant leaking out, whereas this one, when you're putting together, a lot of it pushes out. Some of it pushes into the ductwork, and over time, some of that sealant's going to be washed away, so you'd be more likely to have leaks with something like that. Feedback on the Jeremias stuff, at least up to like the 18 or 20 inch size, is that it's much quicker to install. So they see up to 50% savings in installation. The Jeremias product has a UL listing up to negative 20 inches of water column, where the other they don't have a listing specific to pressure drop. So here's some different configurations. You can do single wall. That would require it either be exposed and 18-inch clear from combustibles, or you'd have to double fire wrap it. Then they offer a double wall product that's reduced clearance. So it has 2 layers of wrap, and then you got to maintain between 1 and 3 inches of clearance to the outside, just depending on diameter. And then they offer a true zero clearance, just has more insulation. For the most part, I see people using the reduced clearance. In most cases, you can get the couple inches that you need to the outside of the ductwork. The zero clearance is great, but from an installation standpoint, the more insulation you add to the product, the heavier it is, and it's just more challenging for people to install. This is an example of what a shop drawing would look like. You can see that they have clean outs, all kinds of fittings to configure it. They have cut pieces to allow flexibility for the installers in the field. Over probably the last 10 years, we've seen a pretty big transition away from your 16 gauge welded ductwork. Even manufacturers that have shops and build their own ductwork, where they're able to make the listed products work, they typically use it. It just eliminates all the field welding, the extra inspections associated with that, the inspections associated with fire wrap. And in the end, it's just a better overall product. So to kind of wrap things up, market overview, who designs what? And so you've got kind of two aspects there. Usually it's going to start with the architect that's going to build the base plan, and then it goes over to a kitchen consultant or a kitchen designer. They're going to lay out all the cooking equipment, how everything's going to work in the kitchen. And as a part of that, a lot of times they're going to select a hood and potentially the fans and makeup air and everything that goes along with it. And then above the ceiling, that falls into the mechanical engineer scope of work. They're going to design the duct layout. They're going to look at what's going to be required for fans, makeup air, what power is available. So it's important that there's communication there. The more communication between the two design groups, the more successful the project is in the end. It's important to remember that from the kitchen standpoint, a lot of times they don't know the specifics of the building or what the duct run is going to be. And so it's just kind of base selections. And so what I like to do when I'm involved in those projects is tell the kitchen design team, hey, here's kind of a base. I'm assuming that it's a single story duct run. We have some offsets. When a mechanical engineer comes on board, let's collaborate. Let's figure out what's really happening in the building. Do they have some extra makeup air from RTUs that we can back out of our makeup air unit? What's the duct run actually going to be? And it just ends up with a more positive outcome for the project in the end. I'll wrap it up by welcoming people to come to Greenheck and check out the products. They have a really nice display center, an innovation center. You can check out the different AMCA test chambers that they have. So feel free to reach out to us at Dorse if you're interested in seeing something like this, and we'd be happy to get you in on a trip. I'll open it up for any questions that anybody has at this point.
Thank you, Ryan. If you want to check your chat, you'll see some of the questions. The first that was asked was about heat recovery coils on the back of a hood system. And I kind of answered a little bit of that from the Greenheck point of view, but you might have some more industry insight.
Yeah, I mean, there's a few companies that have done it. Usually the extent of grease control before you get to one of those is so extensive that it's cost prohibitive. And I've seen some in older buildings, and they've become major fire hazards because of maintenance and those type of things. So as beneficial as it could be, because how contaminated the exhaust airstream is, we don't see very much of it.
And we had another question regarding MAU with DX heat pump, which you touched on with the model RV. So I was able to provide some details in the chat regarding our 5 to 30 ton model RV air source heat pump, which should be going down to 3 tons and roughly 600 CFM on the low end with a new cabinet we're getting in August. I was actually going to respond in the chat to the next question. But for demand control ventilation, do the hood, fan, and makeup air need to be provided by the same manufacturer?
They don't have to be. I mean, from an integration standpoint, when possible, I think it's a good idea, but they don't have to be. It just, that's where, reach out to me. I'm happy to look at the control sequence of whatever you have for the demand controls and make selections for exhaust and makeup air that will work with anything.
Yeah, and that's kind of something that's wonderful with the Greenheck system, where we can provide all of the components and we can ensure that it's all going to communicate properly. I've worked on numerous projects in my life where the hood manufacturer was someone else, and then the engineer would spec and the contractor would purchase the Greenheck equipment for fan and makeup air. And there was always a disconnect of what the expected output signals were for maybe the hood controller to our equipment. So it can be done. It's just one extra step of communication from who's providing the hood controls or at the hood and the fan. So that's what we like to say, we're a single point source. We can do it all and ensure it's all going to work. And then you have Ryan, who's been doing this for over 2 decades, who will doubly make sure it's all correct.
Yeah, I mean, the usually the hood controls are going to come with the hood. I think the biggest part of the coordination is going to be who's providing VFDs, if they need VFDs, are they EC fans? What power is required? Do we have the turn down capabilities on the stuff that's selected? So wherever possible, integrating into one system is going to make it a lot easier for field coordination and supporting the electrician. And then for the life of the system, the restaurant owner has all the components from one manufacturer. So any questions, warranty, performance issues, it's one source for everything that they need.
Excellent. And I wanted to touch again, I put it in the chat, and I meant to say it at the beginning. Ryan works with our Dorsey engineering support team and our construction team. So if you're working with Scott, Blake, or myself designing a project, Ryan is going to be working with us on the kitchen system side of things, and he will follow it all the way through that job being priced to the contractors, to ordered and installed, and site visits if necessary. So he's doing a true cradle to grave service for the kitchen ventilation system. He's not just laying it out and that's the end of his responsibilities. He's going to lay it out, submit it, and make sure it's installed correctly and do anything the contractor needs for support. We do have another question here. How common is kitchen equipment that have air curtains? Are there any additional considerations for those?
For kitchen equipment that have air curtains, I'm
Are you
not too
referring
familiar with the specific kitchen equipment. I would say the air curtain on the hood is common on pretty much all of the hoods, unless they're doing like the DOAS or RTU approach. If you have a specific application, email it over to me and I'll take a look at it. I know that we're seeing a bit more eventless equipment from manufacturers. So maybe you're referring to something that's incorporated into a ventless application. What I'd always recommend for those is just look beyond the marketing material. Jump into like their OIMs and those type of things to see what the requirements really are for exhaust and heat and those different type of things.
Yeah, I have seen some systems or some designs in the past where someone would kind of try to create a true separate air curtain to, I guess, aid in capture or air escaping. But I think what you might be referring to is what we call the external supply plenum, right? That makeup air that's dropping just outside of the hood itself. That's typically tempered or heated. That will be, pulled back into your hood. So if that's what you're referring to, if we're not answering your question all the way, please comment or send us an email and we'll make sure we answer your question fully. So with that, we've hit the top of the hour. We'll hang around for a couple of more minutes, but Ryan, thank you as always for everything you do. Great presentation. And join us next week where we will be touching on the model RV, RVE, RVC, our high percentage outdoor air handlers, which can also be used for those heat pump kitchen makeup air explanations or applications. All right, we'll let everyone go. We do have another question here. So again, we're going to stick around for a few more minutes. With demand control ventilation, does the airflow at the external plenum need to vary with the exhaust?
It does. Yeah. So they'll modulate together to maintain that balance for both exhaust and supply. So that's all part of the configuration and the logic of the control panel.
Yeah, it's a kind of a wonderful system Greenheck has. And again, when Ryan selects the equipment for this, we'll have a VFD or an EC motor on the makeup air, and then typically a VFD or an EC motor on that exhaust fan, and the logic of the controller will just track each other as necessary, and it's a nice system. All right, any others? I like it when we get questions. It means people were paying attention.
Yeah, I'd encourage people, and I know a lot of the stuff's included in CAPS, but feel free to reach out with the applications. Usually I can turn around a design, uh, you know, regardless of how much information you have to start, I can usually turn around a design on a hood system within 24 hours, get you some spec sheets or drawings, whatever you need. And then as the design progresses, we can continue to make modifications and updates specific to the project requirements. So don't feel like you need to absorb all this and do it yourself on CAPS. That's what I'm here for. And it's important to me to be involved in the project for a successful outcome for all of us.
And Brian has some great questions here, and I know I've had this question many times. Can you see the chat, Brian? I'll read it for everyone else if you can't.
Yep.
If there are
Okay.
multiple hoods on a single PCU and MAU, does the makeup air unit to each hood need to be varied independently?
It's if you have one makeup air and one exhaust, that's typically going to be the application when you have a PCU. Then they'll balance the air to each of the specific plenums, like using volume dampers and those type of things. And then it'll modulate up and down together as a group. But yeah, as a part of finishing up a project, we like to go out and verify that we have the actual airflows that we've designed or ideally within 5%. And that's where we use the balance dampers on the supply plenums. And in a case where you have multiple hoods on a PCU, we'd potentially have exhaust blast gate balance dampers where we'd be able to go in and also balance those hoods to the design CFM.
It's a fun question. I get that one once a year, it seems like.
Yeah, there are some systems like more advanced DCV that have modulating exhaust dampers where you could potentially modulate each of those hoods independently. It just, again, a more advanced system. We do have access to stuff like that. If you run into a project where they want to do something like that, reach out to us. We have options for that.
And everyone keep in mind that Ryan is based out of our Seattle area office. He is happy to come by and give your team a presentation or talk about an application. And he just got back from an Eastern Washington tour. I believe that was last week.
Yep.
Visiting customers. So, he'll cover the state and do what's needed. And I'm signing you up for a bunch of work, Ryan.
That's great. I like to be busy.
Yeah. So we're here to help, and we don't expect everyone to remember everything we've talked about, but just remember Dorsey does have our own in-house expert who can help size, budget, and design systems for you. So with that, we're going to let everyone go, and hopefully we see you all next week. Thanks, Ryan.
Thank you.